So good afternoon, ladies and gentlemen. We will start with today's scientific afternoon, yes? And today's speaker is Dr. Tina Škorjanc. I will briefly introduce her, and I will briefly introduce also the topic of today's talk, today's seminar. So, the 2025 Nobel Prize for Chemistry was awarded to Professor Susumu Kitagawa from Kyoto University, Japan, to Professor Richard Robson, University of Melbourne, Australia, and to Omar Yagi, University of California, Berkeley, USA, for their pioneering work on metal organic frameworks. What are these materials really will be explained by Dr. Tina Škorjanc, who has two links with this Nobel Prize, at least two links. She's working within this area, this field of research, and she recently spent a year at Professor Kitagawa's institute at University of Kyoto. So, born and raised in Maribor, Tina Škorjanc left her hometown at the age of 19 to pursue a Bachelor of Science degree in chemistry and biology at New York University's campus in Abu Dhabi, United Arab Emirates. After graduating in 2015, she obtained a global PhD student fellowship to pursue doctoral studies in chemistry at New York University in New York and Abu Dhabi. Tina joined the Material Research Laboratory at the University of Novi Gorica in 2020 with Marie Curie postdoctoral fellowship, and in 2023 she secured a Japanese postdoctoral fellowship which took her to Kyoto University for a year. She is now an assistant professor at the University of Novi Gorica and teaches chemistry at the School of Environmental Sciences. Her research interests focus on porous polymers and covalent organic frameworks for various applications ranging from water purification to the biomedical field. She has co-authored over 35 scientific papers and several popular science articles. It's my pleasure to invite Tina to the podium to give us insight into the latest Nobel Prize. Tina.
Thank you. Shalom, it's yours. Okay. Thank you, Matthias, for this introduction. Thank you, everyone, for coming. I know it's a late afternoon and you'd probably prefer to be somewhere else, so I appreciate your time. So, as Matthias mentioned, I work here at the University of Novi Gorica in the Materials Research Lab. And in this presentation, I will tell you a little bit about the Nobel Prize, which was given in the chemistry field in 2025. So I was indeed at Kyoto University, where one of last year's Nobel laureates comes from. And so we are still in touch very much with the scientific community at this institute, which is part of the university. So last year I got a video which shows a moment when this Nobel Prize was revealed, and you will see the reaction of some of the group members that I was a part of. So hopefully this is gonna work. Oh, there is no sound. Okay, well, then just a picture. This is Emily. We started around the same time. She stayed for 2 years. And this is my boss, Professor Shuhei Furukawa, who's actually a student of Susumu Kitagawa, last year's Nobel laureate. Okay, so these are the three scientists that contributed to the field of metal organic frameworks and were awarded the Nobel Prize in Chemistry in 2025. As Matthias already mentioned, they come from 3 different countries. Susumu Kitagawa is a Japanese scientist and works in Japan still. Richard Robson is an Australian citizen, and Omar Yagi was actually born in Jordan, but then at the age of 15, moved to the US to pursue his education and now works at UC Berkeley. So here I've written some keywords that you may have heard of or may have not, but throughout the presentation, hopefully, it'll become clear what all of this means. So Susumu Kitagawa is credited with the discovery of the so-called breathing moths. Richard Robson was the one who worked on the early coordination networks. So this was the so-called first metal organic framework, even though it was not called this way. And then Omar Yagi is the pioneer of reticular chemistry, which extends beyond metal organic frameworks, and is also the one who discovered, he and his team, of course, one of the most famous examples of MOFs, the MOF5. So why are MOFs, metal organic frameworks, so important that they deserve to receive a Nobel Prize? So it says here that the Nobel laureates in chemistry have created molecular constructions with large spaces, that's a crucial word, through which gases and other chemicals can flow. These constructions, metal organic frameworks, can be used for all kinds of things, such as harvesting water from desert air, capturing different gases, including CO2, storing gases, including some toxic ones, and catalyzing chemical reactions. So first, we will go through a kind of a history journey, how the development of MOFs progressed. And after that, we will focus also more specifically on applications and the types of uses that these materials have found. So this is an analogy. If I was to explain what a MOF is to a person who has no background in science, I would say something like, imagine a big apartment building where all the apartments are studios of exactly the same size. So the apartment building has these compartments, and these are the porous features of MOF. So the pores where different molecules can find their home, temporary home, and then when something changes, these molecules can leave their home, and then reversibly, they can also return and leave again. So this is a place where a water molecule can stay for some time and then leave, a place where a CO2 molecule could reside for a certain period of time and then again be released from the material, or a toxic dye molecule could also be captured temporarily. So this is what a MOF is in schematic terms. So in order to make a MOF, you need two constituents. One of them is a metal ion. There's all kinds of metals that have been used to construct metal organic frameworks. In the early days, these were indeed metal cations like iron 3+, zinc 2+, and so on. But in the later days, when MOFs got more complex and there was a greater diversity of these materials that was developed, these were not only individual metal ions, but rather metal clusters. And I will show you some examples of these a bit more complex architectures later on. So in addition to this metal component, you also need an organic linker, which could have different functional groups. For those of you who know some chemistry, these could be, for example, carboxylates, pyridines, and so on. So these will combine into a porous structure called metal organic framework through a series of coordination bonds. The key thing here is not just coordination chemistry, because this was well known in the field of chemistry even in the early 20th century. But what is really important is this void space, these cavities, which can be used to store, capture, and do useful things inside of them. So now that we know roughly what schematically how a metal organic framework looks like, we will start with a bit of history. So even though in the official Nobel portrait series, Professor Kitagawa is represented first, this is not really following the historical line, because Richard Robson is actually an older scientist who started working on, I would say, the precursors of metal organic frameworks earlier on. So if you are a chemistry teacher like me, you would use this kind of ball and stick models. Let me see, yes. To teach students about things like molecular geometry and, to try to encourage them to build their own molecules, right? So apparently Richard Robson was also a chemistry teacher, except that in the early 70s when he was teaching these classes, there was no plastic, so they had spheres and sticks made of wood. And so he realized that in order to make a molecule, what you need is to drill holes in these spheres that represent atoms in specific positions. Otherwise, the molecular shape would just be represented incorrectly. And so this was just an idea that he had, and later on developed into the first, well, now we can say metal organic framework, even though he didn't use this name. So if you look at the structure of a diamond, which is shown here, so this is a schematic of a diamond, and this is the atomic model, it's composed of pure carbon atoms, and they are linked to each other in such a way that they form tetrahedrons. So each carbon is linked to 4 other carbon atoms in a geometric shape that we call tetrahedron. And then Professor Richard Robson asked himself a question, what if instead of individual carbon atoms, we would have molecules at these positions? And that's how the structure that you see here was actually born. So he combined, instead of carbon atoms, he had copper-1 ions, and then he linked them together in this extended network with these organic linkers. So this organic linker has functional groups that are called nitriles. So this is carbon triple bond nitrogen. And these form coordination bonds with the copper ions, and they form these extended structures. He later also showed that you can fill these cavities. This was a new part at that time. You can fill them with things like anions, and you can also exchange these anions one with another. So most scientists in that time, so in the 70s and early 80s, would expect that this reaction would give an amorphous material, a very randomly combined series of metals and organic linkers, and certainly people would not expect that these materials would have cavities, that it would be porous, right? So this was a kind of a surprise. And it was a new way of constructing materials. But of course, this was just the beginning, and this structure also had many problems. So one of them was the instability, right? So these materials would disintegrate when exposed to various solvents or even just water. They would be thermally unstable, and this is certainly a problem, right? It's not the material that you want to sell. There was no clear purpose at that time that these materials would have. It wasn't obvious in which applications they could be used. And because of these points 1 and 2, it was also very difficult to obtain research funding to develop these materials further. But at this stage, the next player, or the next Nobel laureate, comes into play, the Professor Susumu Kitagawa, who apparently was not only into chemistry but also into philosophy, and he tried to see the usefulness of useless. So even though these early coordination networks did not have a clear purpose, or there was no application immediately obvious that these could be used for, he did not give up. And rather than seeing this as a frustration, he saw it as a challenge, right? And he set himself a goal of developing a material that would overcome these problems. So it would be formed in the same coordination chemistry manner, but it would also be more stable. So one of the materials he developed is shown here. This happened in 1997, and it was a major breakthrough. So this metal organic framework, so the term MOF was already coined by then, was composed of, it could be made with different metals, so with zinc, cobalt, or nickel 2+, and these metal centers, so here we still have metal cations rather than clusters, would be linked together with a molecule called 4,4-bipyridine. So because I suppose some of you are not chemists, I will draw this molecule on the board. Okay, so these nitrogens are the ones that can form coordination bonds with any of these 3 metals. So this material was indeed stable, so it overcome some of the challenges that existed before, and it was also useful in absorbing different gases. So unlike the previous structure I have shown, this does not really have a cavity, but rather it has a channel, right, that is here labeled in yellow color. And so this is where if you put this in atmosphere of a particular gas, like, I don't know, CO2, methane, or whatever, the gases will physically absorb into these pores, into these channels, and then you can also release them and then bind them again. So this is what is meant by the term reversible adsorption of gases. Right. So another major contribution of Professor Susumu Kitagawa was also the so-called soft crystals. So at that time, MOFs were already accepted by the scientific community, but the problem was still that they suffered from competition from zeolites. Zeolites are another class of materials that is also porous, so it can also store gases, for example, but they are purely inorganic, right? So they are made up mostly of the atoms of silicon, aluminum, and oxygen. And so many scientists would ask, why would you want to construct something as complex as a metal organic framework when you can do the same thing with zeolites? You have not much problem with stability and you can achieve the same goal, right? So there was still some challenges to be addressed. There was still some explanation to do to show in what way MOFs are different or better than zeolites, for example. Kitagawa decided to work on this question. So what advantages can MOFs offer that the competitive zeolites cannot? And the answer is actually in this figure. So this is showing a framework of some metal organic framework, and the orange spheres represent some of the gas molecules that are trapped in the pores, right? And what you can see is that when you release these gas molecules, when you remove them from the pores, the structure of the MOF actually changes slightly, right? So this shows that the materials are flexible to some extent, and this is something that zeolites cannot do, right? Zeolites are hard materials, and they cannot exhibit this kind of behavior. So softness was one of the advantages that at that time was explained as the reason for which MOFs are superior or different, but still useful, even though people used and worked with zeolites. So the first time that the term metal organic framework was used was actually in a publication published by Professor Omar Yagi. This was a very short paper that was just 3 pages long, and by now has reached several thousand citations, and was published in 1995. So here you can see that between these layers, we have trapped molecules of pyridine, which in this case acts as a guest, right? So this is the molecule that we can reversibly capture in these between layers of the material of this metal organic framework. Okay, so in one of the early slides, I have written that Professor Yagi's major contribution, and also the reason why he was part of this Nobel Prize, was the so-called MOF5. So here there is some context to that. So here, MOFs are becoming more complex, as you can see. Instead of having just a metal ion, we actually have a metal cluster, which is formed in situ. So we basically, the way this is synthesized is you take a metal salt and organic clinker, and then while this is cooking, the cluster is formed and the MOF crystallizes. It is not really feasible to synthesize these clusters on their own and then form metal organic frameworks. So this is a classic example of a metal organic framework. It contains zinc ions, and as you can see in this cluster, each of the zinc ions is linked to 4 oxygen atoms that are part of the linker. So the terephthalate linkers, this is just a benzene with 2 carboxylates. So it looks like this. Well, should be like this. So 2 carboxylates. And the white spaces that you see here, this does not really represent, the yellow spheres you see, this does not really represent any particular gas or metal or anything. This is just to show the cavity. It's to emphasize the cavity size. So why this moth was so wow? The reason was its very large surface area. So if you have a gram of this substance, the total surface area of this material would be the size of a soccer field, right? So nowadays there are moths with surface areas as high as 7,000 square meters per gram. So 1 gram would have a surface area of 7,000 square meters. And this value is much higher than what zeolites can achieve. So this was yet another reason or another point where moths could be proven superior to zeolites. So they can have higher surface areas than zeolites, and they can also exhibit this softness, this soft nature. But this story with moth 5 doesn't end here. It's not just a material with a very large surface area. This is also the first time that moth family was created. So basically, Professor Yagi's group showed that using the same metal cluster and structurally similar but not exactly the same linkers, they can create a family of metal organic frameworks, and they can tune the properties of these materials in a predictable way, right? So the original moth 5 used this linker and had this shape or molecular structure. But then if you use a slightly longer linker, the cavity size increases dramatically. You can also chemically modify this linker. For example, you can introduce different functional groups like halogen atoms, like you can introduce some hydrophobicity, and this will change the properties of the materials. Still, all of them have the same metal cluster in their structure. And this kind of predictability, where you can basically on paper or on a computer design a material and know its crystal structure, was not there before, right? X-ray crystallography was present much earlier than moths were around, but it was difficult to establish the connection between the crystal structure and the chemical composition of molecules, right? It was not easy to predict one from the other, and this is what changed with metal organic frameworks. So this is a summary of the contributions of these 3 researchers. So the story started with Richard Robson, an Australian professor who was the first one to make networks similar to diamond, but unlike diamond, which is a very compact and very hard substance, these materials actually contained cavities. And you could put different anions or different gases in them. But of course, these were early examples, so they had lots of trouble, like, for example, the stability issue. Later, in the 1990s, Professors Kitagawa and Yagi continued this work, and Professor Kitagawa made his two most significant contributions were making a material which has channels and not just cavities, and then also demonstrating that these materials can have a soft nature. So depending on what gas they contain or do not contain, their shape can change. And then lastly, we have Professor Omar Yagi and his famous MOF 5 that I was just speaking about. So materials with really high pore volumes, high surface areas, and then also the MOF families. I forgot to mention the term reticular chemistry, which also came with Professor Yagi's contribution, and that refers to the connection between the chemical composition and the structure. Okay, so if you want a Nobel Prize, what does your discovery need to contain? First, it needs to change how scientists think, and this has happened, and hopefully by now you agree with this. But it's not enough. This point is not enough. It also has to demonstrate a broad impact, and it has to enable new discoveries. And so now I will focus a little bit more on these 2 points, so the applications of these materials. So here we have examples of 6 MOFs that were each used for a different purpose. For example, this material was used to capture water in the desert at night, and then when sun comes out during the day, you can release these water molecules. Now, why does this work? Because the organic linker in this particular MOF 303 can form hydrogen bonds with water. So it's a pyrrole molecule that can bind water molecules, and there is also this cooperative binding mechanism, so that once the first water molecule binds, the second one, binding of the second one becomes easier, and so on. And that's why the water uptake is significant. These MOF materials can also be used for catalysis, such as this one, which is an iron-based metal organic framework. This one has also been used to store different gases because it has very large cavity sizes. Some of these MOFs have also been used to capture pollutants from water. For example, this ZIF-8, which is zinc-based MOF, and it contains also the 2-methyl-imidazole linker, which can form coordination bonds with rare earth metal cations, and it is selective for these as opposed to sodium or potassium or calcium ions because they have a higher charge. This is a metal extraction. The pollutant absorption one is actually this one, which I skipped, UiO67, which has a hydrophobic linker, this biphenyl moiety that you see here, and a zirconium cluster. And so because of these biphenyls, the structure is quite hydrophobic, so it can form interactions with, for instance, perfluorooctanoic acid and the other PFAS molecules. So these are fluorinated molecules that are quite toxic and shouldn't be present in drinking water. There are strict limits as to how much is allowed. And then as the zirconium metal cations in the structure, they also form ionic interactions with carboxylic acid functionalities in PFOA, for example. And then this one is used for CO2 adsorption. It supposedly has a very poor size dimensions that fit the CO2 molecule directly, and it apparently even being tested in some factory in Canada for industrial level applications. Gas storage, I believe I have mentioned. This one was tested for hydrogen gas storage. Mostly MOFs work well for hydrogen storage at low temperatures, unfortunately not at room temperatures. Okay, so now let's say that you have felt somewhat inspired by this story and you are eager to go to the lab and make a metal organic framework by yourself. What do you need? This is roughly one of the protocols that you could follow. So you would certainly need some metal salts and some organic linkers. These are the two main components of a MOF. And you would have to stir these in some solvent. So you have to be careful which solvent you choose, because if one or the other of the two components don't dissolve, you will have trouble. Then traditionally MOFs are made in such a way that this reaction mixture is transferred into a Teflon liner, and this is then placed inside such a reactor, an autoclave reactor, which is then heated in an oven. And these reaction times vary, of course, but they are usually several hours or even several days. And then when you're done, when this time is over, you take this out. It has to cool down. You open it up, and hopefully you have your product there, but certainly it is not pure. So you have to do several steps of washing with the goal of removing any remaining metal ions, organic linkers, or also other impurities that may have formed. And then if you're very lucky, you have your products. So this was a traditional way of making MOFs, and many of my colleagues in Kyoto University were still following this kind of route, right? But over the time, of course, other methods of MOF synthesis have been developed. So if you want to make it faster, you could try with a microwave-assisted synthesis. So you have a microwave reactor, and your reaction happens there. Ideally, this would reduce the time, but it may not work every single time. There is also mechanochemical synthesis. So you basically use a mortar and a pestle, just like in the kitchen, and you grind your starting materials and possibly put them in the oven afterwards. there is, of course, the goal, the ideal situation would be room temperature synthesis, but that certainly depends on reactivity, and it's not nearly always possible. There is also electrochemical synthesis where you don't actually use a metal salt, but instead you can use the actual metal, so piece of metal. You then form in situ the metal cations from that metal, and then the reaction with the organic linker happens. So these are, I guess, more exotic, but they have been used in the preparation of MOFs over the last, I don't know, several decades. So, of course, patience is key. What I've shown here is an optimized protocol, but if you are developing a new MOF, you could get stuck at any of these steps for months easily. So the first step is linkers have to be synthesized. That already can be quite challenging, depending on how complex of a linker you want to design. You may be able to buy it. In that case, you're very lucky. But most of the time, or sometimes, this is, depending on what you want to make, this is not possible. And then the next step is the actual MOF synthesis, which again takes on the order of hours to days. In the next step, you would ideally want to grow MOF crystals, because then you can elucidate their structures using X-ray diffraction, and then you have to, of course, do something with these materials. So you could make membranes, you could test them for the absorption of gases or pollutants, or you could even use them in biomedical applications. So after you have synthesized and purified your MOFs, then you also have to characterize them. And there's a whole range of different techniques that we use to do that. So, of course, porosity is very important, so it matters the surface area, the pore size distribution, etc. So you do gas adsorption measurements to characterize this MOFs in this way. Of course, you also do X-ray diffraction in order to then get the structures of the materials you have synthesized. We use infrared spectroscopy to see which functional groups have reacted, which ones have not, and so on. And then also thermal analysis with thermogrametric analysis setup. We see how thermally stable the materials are. I didn't emphasize this point too much, but the earlier structures of MOFs were not particularly thermally stable. And so later, when they achieved thermal stability up to, say, 300 degrees Celsius or 350 degrees Celsius, this was already like they were already happy with that. And then, of course, you also want to know how your MOFs look like, so you would often do scanning or transmission electron microscopy to see their shapes, morphology, and so on. So I put in this slide, even though it has a lot of text, because I wanted to share a bit with how MOFs get their names, right? In that slide with applications, I have shown you some names that may have looked strange, like UIO 67. So this table explains this a little bit. Basically, this is the early names are just MOF plus a number. But then later on, people started to name their metal organic frameworks based on the institution where they worked. So, for example, some MOFs were discovered at the University of Oslo. And in Norwegian, that's how you call University of Oslo. And that's where the name UIO plus a number came from. Some other MOFs, also a very famous series of MOFs, was prepared in France, so in the materials of Institut Lavoisier. So they're called MIL plus a number. It's an abbreviation for the name of the institute where they were first prepared. H-cast MOFs, also very famous. They were made in Hong Kong University of Science and Technology. So basically, if you make a new MOF, you can name it as you wish, right? You can follow any of the standard, say, nomenclatures, or you can also use U and G as a name. Okay, so in this slide, I wanted to share a little bit about materials related to metal organic frameworks and how they are different from MOFs. So I don't really work with MOFs, so I'm not an expert, but I have done lots of COF synthesis and tested COFs for various applications. So COFs are related. They are called covalent organic frameworks because they contain no metal cation. So they are purely organic structures. But they have some similarities to MOFs. Like they also have high surface areas, though not as high as MOFs. And because they are organic, they tend to be more biocompatible, for example. So yeah, they are to some extent similar to MOFs. Then there are zeolites, which I mentioned a few times during this presentation. So they are similarly porous materials, but their surface areas are lower than those of MOFs, and they are purely inorganic. So there is no organic linker in these. It is just a mixture of silicon, aluminum, and oxygen. Then we have activated carbons, which are cheap to produce. They have lots of applications. If you're traveling to an exotic place, you get a bit of food poisoning, you could take this to hopefully feel better in a few days. They also absorb pollutants from water, but they are non-specific, so they will just absorb anything, right? So during my PhD, we used to test these coughs for water purification purposes, and we would also do a test with activated carbon as a comparison, right? And then we would be very lucky if our material would absorb more of some pollutant than activated carbon. And then there is also silicate, which is similarly to zeolites, inorganic material. It has some tunability in the structure, but not nearly as much as metal organic frameworks. So the diversity is less than in MOFs. Okay, so obviously MOFs are important. They have won a Nobel Prize, but this story is not ended. There is new papers on MOFs coming out literally every day, and there are still many challenges that these materials face. For example, many times people say that the synthesis of MOFs is just too expensive, so it will never reach the actual industrial scale applications. Sometimes they say they are toxic because these heavy metals in their structures are problematic. They are also sometimes difficult to characterize. So we have to use all these different techniques to get most information that is possible. They can be mechanically fragile, and still even today, some are not stable in water in solvents and also not thermally stable. So there is still lots of work that can be done in this field, and this is still a very, very active field of research. So the summary of this presentation in 5 points, what I hope you would take away from this talk is that MOFs, or metal organic frameworks, are materials composed of metals, metal cations to be more precise, organic linkers, and these two entities combine in such a way that they form a porous structure. And they have large surface areas, and their structures are very tunable, so you can adapt them to the needs, or you can tailor them to the application that you wish to study. They have found applications in various fields, anything from water harvesting to catalysis to gas capture, pollutant removal from air or from water, biomedicine, so imaging, all kinds of things they have been used for. There are still challenges in some of them, especially when it comes to stability and also scale, right? It is not always possible to generate these materials on large scales. Sometimes you're lucky with just a few milligrams, right? That's just the reality. And of course, last year's Nobel Prize honors these 3 scientists, Susumu Kitagawa, Richard Robson, and Omar Yagi, but also, of course, honors MOFs and chemistry as an architecture. So I wanted to put this picture because this is a commercial metal organic framework that you can buy from Sigma Aldrich, where we many times buy chemicals from. So this is one you can actually just order online. So with that, I would like to thank you for your attention. Many thanks for coming all the way to Vipavi. And if you have any questions, of course, I will try to answer.
Thank you, Tina. That was quite interesting insight into the new fields of chemistry, really interesting. So I really would like to address now the audience for questions.
Artini. Very nice talk, very much. You enjoy.
2 questions I have actually. The question number 1 is what is the typical number of atoms in the unit cells? I know they vary, but what is the range? Could you say that? Then I was a second question.
Yeah, actually, the pore sizes are very different. Pores can be even up to 10 nanometers. So you can even capture proteins inside these pores. The atoms, the number of atoms in a unit cell on the order of thousands, I would say. Yeah.
Thank you. And the second question, I see.
Am I enough loud? I think enough loud I am. Thank you.
Okay. So my question is the linker that you have shown, even the shorter one, to the best of my understanding, should have some rotational flexibility, right? So it can rotate
Yeah.
around the
This is a
bond.
terephthalate. So terephthalic acid comes from
Yeah.
terephthalic.
So if the linker is even longer, so there will be some polymeric flexibility in these networks. So that upon the change of external conditions, there should be some range of external conditions upon which this network morph changes sizes. Has something like that been detected?
If you were to have more than one phenyl ring here, they would not all be flat. They would be partly rotated because of steric torsion. So yes, that would influence the length of the molecule and also, yes, the flexibility. That's why I showed a little bit about softness of MOFs. So these structures are flexible. Not all of them, but some of them do exhibit this behavior. Yes.
So upon changes of external conditions, they may shrink and they may release the gases that they was that studied?
They can shrink or they can expand. Yes, actually, this was one of the reasons why Kitagawa's group, Kitagawa got the Nobel Prize, right? So, yeah.
Thanks.
You're welcome. Thank you for the question.
Yeah, sure.
Thanks. Very cool talk. I think you know that I know almost nothing, so I think the question is super stupid, but I ask anyway. When I look at the structures of those things, they look like a graph to me. So I think about graph optimization. So something like some linking algorithms, recommendation algorithm, and theoretically you can actually build infinite long graph. So what actually limits the building like a huge structure? And also, since I have no clue, so when you build it, so let's say you have one of the morph structure, usually what's the dimension? I guess you mentioned about the surface area, but what's the dimension and the length?
Sure. Yeah. Okay. I don't think it's a stupid question at all, right? So you would get crystals of various sizes. If you get something that's a centimeter in size, you would be very lucky and very happy as a PhD student or as a researcher, right? Most of the time crystals are much smaller, but always or generally the goal is to find crystals that are big enough that you can mount them on an X-ray diffractometer. Because if you cannot do that, then it's really hard to elucidate their structure, right? So the goal is to get crystals big enough to mount them on this X-ray diffractometer, single crystal XRD. If you're not managed, you can measure powder X-ray diffraction, and there are ways to also get structure from that, but it's single crystal is usually preferred. So that's the physical dimension. And then you asked another question. How large it can grow? Hang on, isn't that the same question?
Basically, yeah, so as it grows, what basically limits, so I think you mentioned the thermal stability and the mechanical fragility, no? So let's say if I have low enough temperature, can I just keep growing and growing?
Yeah, so what will determine the particle size will be things like concentrations, the type of solvent that you use in the synthesis, whether you have added some modulators. So there are parameters that you can vary in order to achieve different particle sizes. Yeah, but this is trial and error. Like people try all kinds of things to achieve the material with the properties that they need. Yeah, not so trivial. Okay.
Thank you for the presentation. I have maybe a general basic question. These kind of materials can be programmed a priori. You have some first principle method, so you can select what to try and which conditions somehow.
Yes. To some extent, yes. So that is the kind of the goal of this reticular chemistry, right? To be able to predict what structure you would get based on the building blocks that you use. Of course, now with the development of AI, there is also emphasis on that in the literature. And maybe that's where your question is headed, right? So yes, there are, for example, there are papers where they use machine learning to try to predict the structures of metal organic frameworks and also try to predict which ones crystallize, which ones would not. So this somehow then limits the difficulty in the lab of trying all the possible combinations. I don't know too much about this field, but there are efforts in this field. Professor Yagi's group, for example, is active in this area. So you can find papers on this topic.
Just a curiosity, but how many structures are available now?
Oh, I don't know, but there are, I would say there are thousands of MOFs. In fact, I went to a conference some years ago, and there was Professor Dinka, who's also active in this field from MIT, and he said, I don't see why people try to design new MOFs. There are so many out there that you can just take one of those and apply them to your application. There is really no need to keep developing new ones, right? Yeah.
Thanks.
Thank you for the question. Anjali.
Thank you, Tina, for a nice and informative talk. I have a small question. Is there any way we can control the pore size of this MOF because it can affect the application?
Yeah, sure. Mostly you can affect the pore size by using shorter or a longer linker, right? So if you use something that's very long, most likely you will get a bigger pore, but bigger pores are also, they tend to collapse. So it is not so easy, right? It is not just saying add more phenyl rings and you'll get a super large pore. But yes, this would affect the pore size. Also, the geometry of the linker could affect. And then also if you're adding some modulators to your synthesis, you can also influence the pores in that way. So yeah, there is quite a lot of wiggle room, but it's kind of a trial and error. Yeah.
So it's mostly random meso, macro that we get. Or we can, if I want, for example, micro, so I can choose that kind of linker or some factor. If I want specifically a micro pore structure.
Oh, yeah, so if you want a micropores, means you want a very small pore, so you should use shorter versions of the linker. Yeah, exactly.
Thank you very much.
Thank you. More questions?
So if not, I'm going to take advantage of my role today and I'm going to ask the last question. Now you said that the cavities can be as large as like 10 nanometers?
Yeah, I read something like 9.7 or so. Yeah, so they used it. So actually, sorry, I should wait. Yeah.
Yeah, well, okay. That is already a size when you can consider these cavities for nanoreactors.
Yes.
Do they use cavities on MOFs for that purpose? You know, to trap different species, and under this special potential condition, you trigger some reaction.
Yes. So these large pores, for instance, have been used to encapsulate proteins and enzymes. So it is a way a nanoreactor, because the enzyme would then catalyze some reaction inside these pores. So yes, this has been done, particularly with these large pore systems. Yeah.
Okay, so Tina, thank you very much for this interesting afternoon. And well, I can announce also that in next afternoon, scientific afternoons, we're going to hear about other Nobel Prizes as well.